Now that we've learned a little bit about solving differential equations, we're going to delve into the first really useful equation that we have here in this section about, applications of differential equations. Now, in the Battle of Seven Potters, this is switching gears. In the Battle of Seven Potters, the Order of the Phoenix made use of the polyjuice potion to create 7 Harry Potters. Let's see, we had Harry Potter himself, we had Hermione Granger, Ron Weasley, Fleur Delacour, Fred George Weasley, and Mundungus Fletcher. They all used polyjuice potion to impersonate Harry in order to act as a diversion. So, and then there's, soon after, Harry uses the polyjuice potion to disguise himself as Barney Weasley at Bill and Fleur's wedding. Well, that's probably going to come up later. And here, we're going to have to review properties of exponents and logs, because that is actually a really important part of the next differential equations. So we have a to the m to the n power. We have a to the m multiplied by a to the n, log base a of n, m plus n, log base a of m over n, log base a of m to the n power, and then log base a of a to the m and a to the log a of m. Let's just not make a big fuss and put all of those properties here for you. All right, so pause here if you need to take these down. We have used most of these properties before, but make sure that you actually get these. In particular, if you look at the last 2 boxes, we have log base a of a to the m is equal to m, and a to the log base a of m is equal to m. And what that should say to you, and if no one's ever said it to you, I'm sorry, but the exponent function, exponential functions, and logarithms, they are inverse functions. So they undo each other, as it were. Okay, so we're going to solve this very particular differential equation. It is dy dx equals ky. And what this says is that dy dx, the rate of growth, or decay, that is directly proportional to the dependent variable. So k multiplied by y is direct proportion with the dependent variable. So I'm going to take you through this. The first step over here, we've got the given dy dx is k multiplied by y. And then our next step is to separate variables. We've been doing this for a few days now, so it's not that big of a deal to see that 1 over y dy is equal to k dx. We're going to integrate both sides. Now on the left side, we have the integral of 1 over y dy. That's the integral of y to the negative 1 power. That's the natural log of y. We have to put that in absolute values because you cannot find the natural log of a negative number. It is not in the domain of the natural log function. So we're going to keep that in absolute values, but don't worry, it's not going to stay there for very long and for some really good reasons. On the right side, the antiderivative of k dx, that's just kx, and then we're putting the plus constant on the side with the dependent variable x. So hopefully this antiderivative kind of makes sense to you. Now here's where those properties come in. We need to solve for y, so we're going to exponentiate both sides. Now there is an intermediate missing step here where we took the exponential of both sides. On the left side, we have e to the natural log of the absolute value of y, which from our properties of logs, because natural log is log base e to the log base e of the absolute value of y, that's just equal to y. On the right side of the equal sign, the only thing that I want to make sure you understand is that the entire right side of the equal sign becomes the exponent. So this is not e to the kx plus constant at the end, the entire kx plus c is the exponent of e. If you're going to use exponentiation as a solving tool, you need to make the entire left side the exponent, and you need to make the entire right side the exponent. On the right side, we're going to simplify. We're going to say e to the kx plus c. That's the same thing as e to the kx multiplied by e to the c. And that property of exponents is shown over here on the left, where we have a to the x plus y is the same thing as a to the x multiplied by a to the y. Or in our case, e to the kx plus c is e to the kx multiplied by e to the c. Now the other thing we did here was move the absolute value away from this by simply saying that the right side is going to be equal to either the positive of e to the kx multiplied by e to the c, or the negative of e to the kx multiplied by e to the c. It all depends on what the value of c is or what the values of y are, because we're going to always make sure that, well, y is positive. And this very last step here, getting to y equals a e to the kx, we do that by making the substitution where a is equal to e to the c. Now, e to the c is a constant, so we're going to simplify e to the c by using another variable to represent it, which is just a. So y is equal to the constant a multiplied by e to the kx power. From here, we would typically solve for a by using an initial condition, but since we don't have an initial condition, we're done. This is our general solution. Notice how the constant of integration is much different than the way we had been seeing him in our previous differential equations. Our constant of integration is that a now, instead of any, plus c. So, like I said earlier, those of you who are used to jamming a plus c at the end of your equations, this isn't going to work for you. So you got to get used to it. So this is the derivation of the exponential growth and decay model. It's used so frequently that most people don't even bother showing all the integration. And you probably won't have to bother showing all the integration. If you see a differential equation in the form dy dx equals ky, in my class at least, you can just jump right to the solution, which is y equals e to the kx. Let's take a look at the notes down here. Since this is a well-known differential equation, it's not necessary to solve or to show all the integration and differentiation. For k greater than 0, the y will increase when x increases. And if k is less than 0, y is going to decrease as x increases. And that's decay. If the value of y decreases, then the equation becomes a decay equation, and we know k has to be less than 0. Basically, positive exponent means growth, negative exponent means decay. Here's a problem. Solve the differential equation dy dx equals 2y, where y equals 100 when x equals 0. If we take that differential equation and we line it up with dy dx equals ky, we notice that it is nearly identical with with k just being 2. So we're not going to bother integrating. We're just going to go right to the solution for an exponential growth model. So we know we have an exponential growth model, k is equal to 2, so the general solution is y equals e to the 2x. It goes by pretty quickly. Next, we're going to use our initial condition to solve for the value of a. 100 equals a e to the 2 times 0, or 100 equals a e to the 0, and we know that e to the 0 power is 1, therefore a equals 100. So our solution here is y equals 100 e to the 2x. So here are some properties of exponential growth and decay. As we saw in that problem, a is always a value of y when t is equal to 0. In other words, a is equal to y of 0, which is usually thought of as the initial amount of whatever is growing or decaying. K is related to the rate of growth. Large values of k means that we have a quickly growing function. And if we have values of k that are large and negative, then we have quickly decaying functions. These next couple of properties are just illustrations. You don't have to memorize any of this stuff, but if y doubles every 5 years, then k is equal to the natural log of 2 over 5. And if y is 50% after 1,000 years, then k is going to be equal to the natural log of 0.5 over 1,000. And you can see there's some simplification here. And that leads us to negative natural log 2 over 1,000. Now there's one particular use for this exponential degrowth and decay, and that's half-life or radioactive decay. So one particular useful application is that half-life radioactive decay. So for example, we know that carbon-14 decays to half its volume after 5,700 years. That 5,700 is called the half-life of carbon-14. And if we know the half-life of carbon-14, we can do some solving to get ourselves into an equation here. We know that k is going to be the natural log of 1/2 over 5,700. We're going to substitute that into the general solution for half-life decay, for exponential decay. Doing some clever algebra work in the exponent, we have that we can simplify e to the natural log of 1/2 over 5,700 multiplied by t. We can group together e to the natural log of 1/2 and then take that to the t over 5,700 power, which is useful because e to the natural log of 1/2 is just 1/2. So for half-life decay, if you know the half-life, then you can actually simplify matters because the general solution is a multiplied by 1/2 to the t over the half-life. Now that's an equation that you can absolutely memorize, but you don't have to. You can always go back to y equals a e to the kt, and that will always get you to a correct answer. Maybe not as quickly, but you will get there. Of course, the consequence is if you decide to memorize this equation, that's just another equation rattling around in your brain. So it's totally up to you. How you work is your business. Here we have a petrified tree trunk contains 12% of its carbon-14 mass. So to the nearest 100 years, how long ago did the tree die? Well, this is half-life decay because we have carbon-14. So let's start with the half-life equation. And then the next thing we're going to do is we're going to say that if it started off with a grams of carbon-14, that means after, right now it has 12% of that, which is 0.12 A. You'll notice that you can actually divide the A out of this. And that gives us an equation that we are going to use our solver for. So go ahead and put the left side of the equal sign as 0.12 and put the right side of the equal sign as 1/2 to the t over 5,700. And the only variable here is t, so we just need to make a guess. Let's say, well, it's definitely more than 5,700 years, right? Because it's more than halfway gone. So let's say, I don't know, 8,000 years. Yeah, 8,000 years. And then, of course, alpha, enter. All right, so I was really wrong. It is 17,435. Now the question says to put this to the nearest 100 years, so I think that is 17,400 years. And that's our problem. Let's go over to our important ideas now. Okay, so the exponential growth and decay model. You don't need to integrate this the long way. You can just go straight from the differential equation to the general solution. Now there's a half-life decay. This is specific to whether or not we have a half-life or radioactive decay. We can use the half-life formula over here. And remember that that comes directly from the exponential growth and exponential decay model. We just had to do a little bit of extra solving to get to this nice equation. If you do have a problem with half-life, then you're going to have to use some kind of a reference in order to get yourself a value for that half-life. If it's ever like a test situation for me, I would just give you the value of the half-life. I'm not trying to test you to memorize, all of the half-lives on the periodic table. That's not what this class is about. And then, of course, it's not necessary to integrate because it is such a well-known differential equation. So let's take a couple of seconds here so you can pause this and write these down if you need to. And we'll go to the check your understanding. So the polyjuice potion can transform a magical person into any likeness, but its effects decrease following an exponential decay curve. How nice. Its effectiveness, ET, is 70% after 60 minutes. So E60 equals 0.7A. How long did the 7 potters have until their polyjuice was less than 50% effective? Solve for the constant K in the exponential decay formula for polyjuice. That's our part A. I'm going to write our general solution in terms of t because this is all in terms of time. So y is equal to a e to the kt. We know that when t equals 0, the potion is 100% effective. And we also know that at t equals 60, the potion is 70% effective. Now we can do some algebra to solve this equation for k. But I'd probably ask you to do this on your calculator anyways. So let's grab the solver. So in the solver, what we're going to do is we're going to put the general solution to this equation. So our general solution, we have y on the left side. So let's put a y there. And on the right side, we have a e to the kt. Okay. Notice I didn't put any numbers here because this will be a lot easier for me to reuse without the numbers. Now the first thing we want to solve for is k. So we're going to put the numbers that we know already. We know that we have 70% starting at 100%. We don't know k, so I'm going to leave that blank for now. And we know that we're at 70% after, I think it was 60 minutes. So the only thing left here is k. Everything else is solved for. So I'm going to take a guess for k. And being that we're looking at exponential decay, I'm going to use a negative value. I'm just going to put a -1 there and push alpha enter. And that gives me a value for k. And I'm going to put this on pause and go right back to the problem now that I have a value for k. And we're going to go to, no, we have to solve for the value of the constant. Yeah, we did that. And the next, how many minutes is the polyjuice potion less than 50%? We write the particular solution, but I think it gets really messy if you put a number up there for k. So I just like to write at the very end here where k is -0.00594. Kind of saves me a little bit of time because that's a long number to write down. The next thing I'm going to do is I'm going to write down the equation, or I'm going to substitute my values. I really should have substituted that 50 in parentheses. And I'm going to stop here and now go back to the calculator. Because in the calculator, I'm going to say y is going to be equal to 50 A is staying at 100, K is going to stay where it is, and the only thing that I don't know is T. So I'm going to hover on T and push alpha enter, and that will solve for these parameter values. So 116.601. Write it in your paper, and remember, like I said, if you are given a calculator, you don't have to show any algebra. Okay, so this is our solution. If you are interested in the algebra that goes behind it, this is what you would do. Divide by 100, natural log both sides, divide by k. Not as difficult to solve, but it is there for you. So the polyjuice potion is 50% effective after 116.601 minutes. Well, that's our work for today. Like all these other applied skills, you are going to need a lot of practice here solving these. We only really went to the easiest solves, and there are definitely some much more difficult ones that you'll have to go over, and maybe we'll put a couple videos on these solves in the future. But otherwise, that's it for today, and we will see you next time.